so atomic structure, this is topic 2 in our IB curriculum. And so there, for the SL level, there's actually a part 1 and a part 2. Okay. And then there's also a separate section for the HL students. So if you're in HL, then you'll be doing kind of all of that. If you're in SL, you will only be doing the ones that say SL here. And there's a part 1 and a part 2. So part 1, we start off today focusing on 2.1. And we're going to do part of this today, not all of it. So 2.1 has to do with the nuclear atom. So we're talking about basic atomic structure. So where are the protons, neutrons, and electrons? What are their masses? What are their charges? How is the atom composed of them? And how does that all go together? How do we write symbols for isotopes, okay, which are atoms that have different numbers of neutrons. So how do we write their symbols? And we're going to be using a specific notation right here, isotope notation. And so we should be able to, from this notation, calculate things like the number of protons, neutrons, and electrons. We should be able to figure out the atomic number and the mass number of the substance. If it has a charge, if it's an ion, we should also be able to figure out the charge on it. And we should also be able to identify our element from this information. So we're going to go ahead and move down here. And the first part, we're going to just recap the subatomic particles. Now, this should not be new information. This is the information that you learned last year in your advanced chemistry class. But our 3 subatomic particles, we have the proton, the neutron, and the electron. Now, in reality, there actually are some particles that are smaller than these 3, but these are the main 3 that we focus on in basic chemistry, okay? And so what I want to point out here is that there are some other terms here that may be new to us, okay? Protons and neutrons can actually kind of be grouped together into this one group called nucleons. And nucleons just simply means that these are the particles located in the nucleus of the atom. And so that's why it only includes the protons and the neutrons. Because if I look down here at this picture, at this key, the protons in this image are the blue particles that have the positive charge. The neutrons are the red particles, and neutrons have no charge, so they won't ever have a symbol on them like that, unless it might be a 0, okay? So I'm going to kind of go through this table. So we have our proton. We have our neutron. Actually, let me switch colors. Let me write them in the same colors that they are on the key. So we have the proton. We have the neutron, and we have the electron. Sorry for my messy handwriting. All right, so relative mass. Now, the actual mass of the protons, neutrons, and electrons, they're very, very, very tiny. Okay, so a lot of times instead of talking about their actual mass, we talk about their relative mass, and that means relative to each other. Okay, so if we compare them to each other, what are their masses? And so protons and neutrons, they have about the same mass. They're not exactly the same, but pretty much the same. So we say their relative masses are the same. They are each 1 atomic mass unit. So AMU stands for atomic mass unit. Okay, and then electrons are the ones that are a little different. Electrons are very, very, very tiny. They're even smaller than the protons and neutrons. So when we compare their relative mass, like when we compare the mass of an electron to that of a proton and neutron, it is almost 2,000 times smaller. And so because of that, we say that it is actually 0. Okay, now in reality, does it have mass? Yes, it does. Okay, it's a particle. It has to have mass. But the mass is so small, it's about 2,000 times smaller than a proton and neutron, and they're already so small that it's what we call negligible. So that's a good word to describe it. Negligible. Did I spell that right? Yes. So negligible, all that means is that it is such a small amount that it does not have any effect on the overall total. And so because electrons are so small, their mass does not affect the overall mass of our whole entire atom. And so we usually say the electron mass is negligible, or if we want to give it an actual number, we say that it's 0. Okay. Now, for the relative charges, okay, I can kind of tell from the little image up here, protons, they are positively charged, +1. Neutrons are no charge or neutral. So you can say 0, you can say neutral, or you can say no charge. I'm going to add it down here because I'm out of room. So 0, neutral, or no charge. All of those work for the neutron. And then the electrons, those are the ones that are negatively charged. Okay, so now that we fill that in, I want to go back up to our information up here really quick. I want to talk about some of the information up here. So the nucleus is very dense, okay? We have to remember, guys, density, if you remember our equation for density, okay, that you guys have learned in past chemistry classes, density is mass divided by volume, okay? And so if you think about it, if I look right here in the center in this nucleus, there is a lot of mass. There's a very high mass, but it's in a very tiny volume, a very small volume. So if I have a large mass in a small volume, okay, if I wanted to pretend to put numbers in here, let's say the mass was 400 grams. I don't know, I'm just making these up. And the volume is 4 milliliters, okay? 400 divided by 4, that's still 100. That's a really dense, that's a really high number, okay? So those are not the actual numbers of the atom, but I wanted to show that as kind of a comparison, because what you need to know is that you need to know the nucleus is dense and it's positively charged. So this area inside here has all of the mass of the atom, okay, or well, almost all, okay, because remember the electrons are so small they're negligible. So because all the protons that have the mass right down here, they are all concentrated right in the center in the nucleus. That makes it very, very dense because it's a lot of mass in a very small amount of space, a very small volume, okay? The other thing that we need to know is the electrons. They are not in the nucleus, okay? The electrons are in the energy levels, okay? They're not in the nucleus, all right? And then this is kind of the most important thing here. Most of the atom is empty space, guys. So all this space in here in between the energy levels, that's what the atom's mostly made of, okay? It's mostly empty space. There's a very, very tiny area here in the middle where the nucleus is concentrated, and then you have these itty-bitty tiny electrons all outside kind of moving around in their paths, in their energy levels, in their orbitals. But everything else is empty space, all outside of the nucleus, in the electron clouds and the energy levels. And so that's kind of the key distinctions of the atom, okay? It's mostly empty space. Okay, the electrons are outside the nucleus in their energy levels. The nucleus contains the protons and the neutrons, and that makes the nucleus very dense since it contains most of the mass of the atom in that small space. Okay, and then the term nucleons right here, again, once again, that refers to protons and neutrons. So if I say nucleons, I'm talking about protons and neutrons all together. And that's just the term for the particles inside the nucleus, which are the protons and the neutrons, okay? So, moving on here, I told you guys we're going to recap how to do these symbols. So this is also not a new concept. This is something that you guys learned last year in chemistry class. It may not have looked exactly like this formatting with the A and the Z and the X, but we did learn this concept, okay? So what we need to know, the way that IB sets this up is they use X to represent the symbol of the element because there is no element X. There's xenon, which is Xe, but there's not just a letter X, so X is just kind of like in math, it's a placeholder here. The other thing we need to know is this A and this Z. So they kind of have it backwards, okay? Because Z down here in the bottom left corner, Z is actually the atomic number, okay? Which, if you look up here, the atomic number is the number of protons in the nucleus, okay? And this is very, very important because this gives the atom its identity. So if I know the number of protons, that means I know the atomic number, which means that I can get a periodic table and I can look up that atomic number and I can identify that element based on that information, okay? The other part in here is this mass number, and mass number is actually represented by the letter A. So that's kind of why I said it's backwards, because the atomic number is the Z. The A is actually the mass number. Okay, so you just make sure you remember that. The mass number is always on the top left, okay? And the mass number, as it says right here, is the number of protons and neutrons in the nucleus. So it's all the protons and neutrons added together. Or I could say it's also the nucleons, okay? Because we just talked about that term includes protons and neutrons together. So all the nucleons, meaning the protons and neutrons added up together, that is this mass number here. It's always going to be a whole number, okay? It is not the same as the atomic mass that is on the periodic table. That we're going to talk about next time, and we're going to recap how we calculate that number. So how I can use this information to help me? Well, I can find the number of neutrons. All I have to do is subtract the atomic number from the mass number, okay? And there's a little trick for remembering this that I'm going to kind of write down here, and you can add it in. There's a little mnemonic device or a little trick. It's called APE-Man, okay? And what this stands for, the APE stands for atomic number, okay? So atomic number, and then I kind of put some signs in the middle here. I put equals. I'm going to put both of these equals. Atomic number equals protons, which also, for right now, equals electrons. Okay, now it only equals electrons for neutral atoms. Okay, when we have ions, they will not be equal. Okay, so just know that sometimes it's going to be APE-Man, not APE-Man. But if it's a neutral atom, neutral means that the positives and negatives balance out. That means we have the same number of protons and electrons. Okay, the other part over here, the man, the M stands for mass number, and this one I'm going to put mass number equals, and it is atomic number. Now this one's not an equal sign, it's minus the neutrons, okay? So the atomic number, or I'm sorry, plus the neutrons. I said that backwards. So the atomic number plus the neutrons. So I'm going to go ahead and fill this in with, nope, I want to switch to blue. There we go. Atomic number, and then this is neutrons. Now, again, this kind of helps you to remember the two things we just talked about. The atomic number, okay, right here. Atomic number always equals the protons, and then as long as I have a neutral atom, it also equals these electrons, okay? The mass number here, it equals the atomic number plus the neutrons added together. And so that's why right here it says that if we want to find the number of neutrons, we can just subtract the atomic number from the mass number. Because if I take this little equation with M equals A plus N and I rearrange it to solve for neutrons, that's what I would be doing. Mass number minus atomic number. Okay, so this is the notation that we use, okay, for atomic symbols. Okay, so we always include the symbol of the element, the atomic number at the bottom, the mass number at the top on the left side. Sometimes you will see a number up here in the top right. If you see that, it's going to be a charge. So it might be like 2 plus, okay, or 3 minus, all right? What that means that the protons and electrons are not equal. That means that some electrons have been lost or gained. If it's a positive charge, like this one I just wrote, that means that it's lost 2 electrons, okay? So that means that if I want to find the number of electrons, I have to take this atomic number and I have to take 2 away because it lost 2. If the charge here is negative, then you gain that number of electrons, and so I would add that number of electrons to this atomic number here. So one thing that I want to point out, and we're going to look at a couple of examples here, is this one. It says we have helium, He, and then it's got 4, 2. Has a mass number of 4 and an atomic number 2. So they just got that directly from reading that. And then from that they can say, okay, well, since the atomic number is 2, that means it has 2 protons. And if I want to find the neutrons, I do the mass number minus the atomic number. So that's the 4 minus the 2. That means there's 2 neutrons in the nucleus as well. Okay. We're going to take a look here at some other ones. So now the last thing that we're going to really talk about today is this term isotopes. And once again, this is not a new term. This is stuff you learned last year in advanced chemistry. But we need to know this definition. They are atoms of the same element that have the same number of protons, but different numbers of neutrons. Okay? That's what makes them different. Okay, and so that also means they have a different mass number. They have the same atomic number, but different mass numbers. So a lot of times you might be asked about what's different about isotopes. And so there's two possibilities: the number of neutrons and the mass number. Those are the two things that are different for isotopes. The atomic number is the same, the protons is the same, the electrons is the same, the chemical symbol will be the same because it is the same element because it has the same number of protons. The only thing that'll be different is the mass number that's up here in the top left, and that's because the number of neutrons are different, and that number of neutrons is included in the calculation for the mass number. So down here on this example, it says the two isotopes shown below are carbon-12 and carbon-14. So they have the same number of protons because if I look down here at their atomic number, they are both 6. That's how I know they're both carbon, because if I look on the periodic table, the atomic number 6 is C, carbon. And so the number of protons are the same and the number of electrons are the same because right now neither of them have charges, so we're assuming that they're neutral, and that means that's the same as well. What's different is right here, okay, the neutrons. This one only has 6. Whereas this one has 8. This one has 2 more neutrons. And they figured that out by subtracting these numbers, okay? Because remember, mass number minus atomic number gives me the neutrons. So 12 minus 6 gave me this 6 right here. But on this one, 14 minus 6 gave me 8, okay? So what you need to know about isotopes, okay? They have the same chemical properties because they have the same number of electrons. Chemical properties are determined by electrons and valence electrons specifically. So they have the same chemical properties, but they have different physical properties because physical properties are affected by things like mass. Okay, mass is a physical property, density is a physical property. So the two most common ones are density and boiling point, because if you have something that's heavier, that's got more mass, that's going to boil at a different temperature than something that has a lower mass. Okay, so density, because if we remember back to that density equation, density is mass divided by volume. So if I have a different mass, that's going to change this density calculation. So physical properties like density and boiling point are different for isotopes, but chemical properties like how they're going to react, how they're going to form chemical bonds, that is not different because that depends on their valence electrons. And since for these example, this is both carbon, they're both going to have the same number of valence electrons, so they're going to react the same way. Okay. There are a lot of isotopes that are what we call radioactive. Radioactive, sometimes people think, oh, that's dangerous. And I mean, it is. You definitely don't want to be exposed to it. But some of them are actually really useful. These 3 that are listed right here, they have different uses. Cobalt-60 is actually used for like radiation and cancer treatments. I'm just going to put radiation and cancer treatments. Carbon-14 is used by archaeologists. This is when you hear that term, if you ever hear the term carbon dating. Okay, carbon dating is like when they're digging up bones or they're digging up fossils and they're trying to figure out how old they are, like how old a mummy is or how old a skeleton is that somebody uncovered. They can use carbon-14 because it's a radioactive form of carbon, and they can compare it to the amount of carbon-12 that's in the tissues, and that ratio will allow them to calculate how old the bones are. And then this last one, iodine-131, this one is used to treat thyroid disease. So it's actually, you can actually drink it. You drink it and it like lights up on scans. And so they allows them to see if you have hyperthyroidism or hypothyroidism, which means that your thyroid's either overactive or it's not active enough. And so a lot of these isotopes, and they're known as radioisotopes, they are dangerous, but they are used in medical and in other fields like archaeology to treat different things and to allow us to have advancements in our technology and in our science, okay? So you have to be cautious with them. You don't want to be exposed to them a lot, but they do have a really good purpose a lot of the times as well. So down here on this practice, it says deduce the number of protons, neutrons, and electrons. So I want to kind of circle in on this word deduce, okay? Deduce means that you are like figuring it out, okay? So if you see the word deduce, that's what it's asking you to do. And so on this one, I'm going to erase, all right, here. On this one, I'm going to look at like number, let's look at letter E. Okay, so letter E, I'm going to write it a little bigger. So it's 37, 17, and Cl. So Cl is chlorine. Now, if I want to find the number of protons, that's always the easiest one to do because it's always going to be this atomic number right down here. So this one has 17 protons, and P plus is the symbol, the abbreviation for proton. Now, if I want to do the electrons, that's the E negative. Okay, that's actually pretty easy as well because on this one, it's going to be the exact same as the protons because there is no charge up in this corner. So they are automatically going to be the same. Now, the last one is the neutrons. The neutrons are the ones that we always have to do a calculation for. You're never just going to be able to look at a number and know them. Because if you remember from up here, we said that we had to subtract the mass number minus the atomic number. So you always do this top number, the bigger one, minus the bottom number, the smaller one. So 37 minus 17, that gives me 20 for the neutrons. And so that is what I would have for letter E on this practice. Now, this next part, we're actually going to wait and do that next class. So we'll finish up part 1, the last little bit, because this part has to do with calculating the average atomic mass using data about our different isotopes. So you just need to make sure that you have done all the little practice ones throughout here and check Canvas for your any other assignment stuff. If you guys have any questions, please let me know in our live call, or you can always message me on Remind.